My name is Vijay Kumar. I'm the Dean of Penn Engineering, and I'm your host for Penn Engineering's Innovation and Impact podcast. Our podcast shares insights from some of the leading experts from around the world. Experts who will bring you the latest breakthroughs and innovations in science, technology, and medicine. Today, we're honored to sit down with one of the true pioneers of artificial intelligence, Yann LeCun, Meta's chief scientist and a Turing Award winner. Yann's work has helped lay the foundation for deep learning as we know it today, and he's at the forefront of thinking about the next generation of intelligent systems. From the realities of AGI to how AI might reshape creativity, work, and even how we govern society, Yann brings not only technical brilliance, but also a vision for where the future is. So thank you again for joining us, Yann.
Very pleasure.
So I'm going to get started with some easy questions, but perhaps you'll have some difficulty recalling the early days in the 1980s when you first started working with neural networks. As I remember, you're the first person to think about using it for understanding writing, handwriting. And I'm just curious, what was the backdrop? What made you focus on this problem? What was your motivation?
So I was not interested in recognizing writing. I was interested in building intelligent machines, and something I got fascinated by when I was an undergrad, and when I realized that people in the 50s and 60s had worked on what we now call machine learning, although in a fairly simplified form. And I was fascinated by the idea that machines could learn, because I didn't think humans, or certainly not me, were smart enough to just design an intelligent machine from scratch. And in the realm of living things, intelligence emerges from learning. And so the idea that a machine could learn, I think, was really fascinating to me from the start when I was an undergrad, maybe around 1980 or so. And then when I really wanted to push this idea, I decided to go to grad school and find people in France that might be interested in those questions. And I had a very hard time. No one was working on this in the early 80s, certainly in France, but even in North America, very few people were working on machine learning, what we now call machine learning, and certainly nobody was working on neural nets. But that didn't stop me. So I kind of figured out, if you want to build intelligent machines, they have to learn. Now, what is the simplest situation where you can train a system or get a system to learn? And that would be pattern recognition, basically, or maybe computer vision if you are ambitious enough. That's the only domain where there was data. It would correspond to perception in animals, which is one of the things that evolved, where nervous systems evolved to do. And then the only thing in the 1980s that you could put your hands on in terms of data, there were only two domains. One was character recognition, OCR, or handwriting recognition, if you're lucky, and speech recognition. Speech recognition already had a lot of people kind of working on the topic in sort of various ways, and that seemed to be kind of a separate field. So I thought recognizing visual shapes, I think, was probably a good domain. And then the next question is, how do you build a neural net that can recognize shapes? It probably has to have multiple layers, which is what got me interested in what we now call deep learning. Wasn't called that way back then. And then how do you structure those things so that they can deal with images? And that's where the idea of convolutional neural nets came from.
So tell us something about back then. Tell us, how are computers? Were they probably were way too slow. And today, we obviously take deep learning for granted, partially because the acceleration and processing speed, the storage, et cetera. Tell us what the 1980s looked like when you were working on this really hard problem.
So in the 1980s, when I was doing my PhD, I had access to what was called at the time a mini computer, which was capable of about one MIPS. Okay, not 1 megaflop, much less than this.
Yeah.
And the amount of memory was very restricted. And this was like a big computer that was, for the entire engineering school I was working in. And so the amount of computational power we had access to was not nearly what we have now, obviously. And also the tools that we had to develop software was not nearly as flexible as what we have now. And so that it was a big effort to, develop a piece of software that was capable of training a neural net, for example. Now we can use, PyTorch, and we have Python and things like this.
Yeah.
None of that existed. Then after I graduated, I moved to the University of Toronto for a postdoc. While I was there, the department bought a new type of computer that Sun Microsystems had come up with called a Sun 4. And when I was recruited by Bell Labs, when I was still a postdoc, my future manager at Bell Labs asked me, we'd like to just order a computer so it's ready when you come. What kind of computer are you using right now? I said, well, I use a Sun 4. When I got to Bell Labs, it was a Sun 4. But the Sun 4 was just for me, whereas at University of Toronto, it was for the entire department. Okay, so I asked my manager what's going on. He said, at Bell Labs, you don't become famous by saving money. So I said, I love this place. But what's interesting is that the time it took at the time to train a convolutional net to recognize handwritten digits was on the order of 1 to 2 weeks, about 10 days or something like this. The time it takes to train the best experimental systems has remained constant for decades now. It's still about a week to 10 days because that's basically determined by how long you're willing to wait to get a new result.
So it's more governed by how patient human beings are.
Basically, and the timeline of how long you're willing to wait.
I have to remember that you don't become famous by saving money.
Right.
I wish we could use that philosophy today. So we talked a little bit about technology and how quickly it's changed. But I'm also struck by the fact that some of your early papers, the techniques that were described, this idea of using multi-layer backpropagation networks and so on to learn very complex mappings, that has still stayed with us. And it's been commoditized. It took 3 or 4 decades, but it's been commoditized. And it's still the heart and soul of deep learning systems. Would you agree?
Oh, I totally agree. What I find surprising is that it took so long for, the majority of the research community to realize how powerful this concept was.
But these multi-layered systems have become more complex in the sense of having more weights, more layers. Mm-hmm. Tell us about the earliest networks you used and tell us about the networks that people are using today.
So the earliest networks, of course, the first experiments were on absolutely tiny networks, just a few dozen parameters and things like this, just because we wanted to understand really what the dynamics of learning was. This was what I was doing my Ph.D. But I did work during my Ph.D. on a 2 or 3 layer neural net that was attempting to do diagnosis of abdominal pain. And so a patient would be described by something like 100 different features. And then there would be something like 20 or 25 different syndromes or diagnosis. And the network was actually pretty big. And we already faced the issue that the number of parameters in those networks was bigger than the number of training samples that we had. And if you were to talk at the time to any computer, every pattern recognition or person or statistician, they would tell you that's crazy. It can't possibly work. If you have more parameters than your training samples, you're going to overfit. But that turned out to be wrong. It's in every textbook, but it turned out to be wrong. We noticed pretty early that although it was a good idea to sort of try to make those networks relatively small, making them bigger actually made the system work better in the end. And this overfitting issue didn't seem to be a real problem empirically. And so the first convolutional nets that I trained when I arrived at Bell Labs had maybe 10,000 parameters, free parameters, and a few tens of thousands or maybe a couple 100,000 operations required to compute the outputs. And at the time, it allowed us to run them pretty quickly on DSP chips. So we had this demo. There's a video on YouTube of kind of me putting a sheet of paper under a camera and hitting a key. And there is a DSP board with a DSP capable of 10 or 20 megaflops actually doing the computation for the neural net. And it was, pretty amazingly fast and robust for the time.
So at what point, so obviously compute was a limiting factor at some point, but then that was no longer a factor. But then data was a limiting factor. I mean, you talked about the difficulty in collecting data with handwritten text, for example. At what point did that not be, that stop being a limiting factor?
So it was always a problem. When I arrived at Bell Labs, the group I was in, led by Larry Jackal, had access to a data set from the U.S. Postal Service that they obtained through a contract with State University of New York in Buffalo. So it was basically images of zip code digits, yeah. and we could experiment with this. And then after that came the NIST data set, which we modified, and it became MNIST, which every student now has to deal with in the machine learning course. So there were very, very few domains for which we had enough data that would make a sort of very sort of heavily learning-based method win. And for the longest time in the 2000s, when I restarted a research project in neural nets and deep learning. The dominant data sets in computer vision had very, very few training samples. This is when computer vision started to get interested in machine learning a little bit in the mid-2000s. And the data sets typically had a few categories, maybe a few dozen or a few hundred samples per category. And so that did not favor learning-based approaches. It favored approaches where you build most of it by hand and have a little bit of tuning in the end. One of the main data sets was called Caltech 101. It was collected at Caltech, obviously, and it had 101 categories, but only 30 training samples per category. And so you could not train a convolutional net to reasonable amounts of performance, level of performance with this. And it's not until data sets like ImageNet. There were a few before that, but they were not. They were kind of peripheral to the interest of the computer vision community. But really, ImageNet is where things changed, because there was all of a sudden there was 1 million training samples and 1,000 categories, and it turns out having more categories is actually very favorable to things like convolutional nets, to deep learning methods, and so that changed everything.
Yeah, this is just one data set, ImageNet, that you mentioned really had a huge impact. And, philosophically, you didn't have to be a computer vision expert anymore to do a pattern understanding, image understanding or pattern recognition, which is a bit scary if you think back. We started in the 80s with your early work. I'm going to fast forward 3 decades to 2015. That was the landmark paper that you wrote with Jeff Hinton and Yoshua Bengio. That has been, as of this morning when I looked it up on Google Scholar, it had been cited 100,000 times, more than 100,000 times. So what was the inspiration behind that paper? Of course, it was the culmination of many years of work, but I just wonder, at what stage in your career were you at that time when you wrote the paper? And did you know that it would be as influential as it is today?
Yes and no. Jeff, Yoshua, and I started a bit of a conspiracy in the mid-2000s. This is when Jeff Hinton came back from the UK to Toronto and was approached by CFAR, which is a Canadian private foundation, to start a program on whatever topic he thought was interesting. And he started a program called Neural Computation and Adaptive Perception, and brought together, in the context of workshops and things like this, a number of people who were interested in sort of, using learning in a bigger way for perception, perhaps using connection with neuroscience. And so basically we said, like, we know those deep learning methods work. They've been extremely unpopular for the last almost 10 years, right? The interest in this kind of started waning within the machine learning community in the mid-90s. And so how can we kind of revive the interest in it? Because we know it works really well. And so the idea was to kind of show that it works experimentally, but also invent new techniques that might allow us to kind of go beyond the capabilities of the system. So we started working a lot on unsupervised learning, self-supervised learning, this kind of stuff. So things that would perhaps allow us to pre-train a very deep neural net, because we thought we couldn't make the neural net very deep, that backprop basically would get stuck or something. So the idea was to kind of pre-train the layers so that they would be in a good starting point, so then we could fine-tune using backprop. Turns out that wasn't actually entirely necessary. You can do backprops with many layers as long as you use a combination of tricks like, ReLUs and good initialization and, all kinds of tricks like this, and what's called residual connections. So there's a paper, famous paper, that sort of proposes this idea, ResNet. The lead author was Kai-Ming He from, at the time, Microsoft Research in Beijing. This is the most cited paper in all of science in the last 10 years. 500,000 citations or something like this.
That's remarkable. Yeah.
Right. It came from China.
Yeah.
This is an interesting thing that a lot of people now, debating about geopolitics of AI, should remember. There's a lot of good things coming out of China, good science. Kai-Ming soon joined us at Meta, at FAIR, and spent 8 years at FAIR, and since last year has been a professor at MIT. Yeah. So that's an interesting story. But what happened is, because of success of deep learning in the late 2000s in speech recognition, and success in image recognition with ImageNet in 2012-13, and then later in 2015, success in natural language understanding, it was clear to the three of us that deep learning was a big thing that could be applied to a lot of different domains, and that the larger scientific community should learn about it. An editor from Nature approached me and said, would you write a review paper on the topic to introduce the topic to the larger scientific community? And that's how this paper came about.
So I want to go forward another 3 years. In 2018, you won the Turing Award, which is, of course, the most prestigious award in computer science. Looking back, well, it seems obvious, right? But in 2018, I think the idea that a machine learning expert or machine learning experts would win the Turing Award, that was a bit extraordinary. I don't know if you agree with me. And
I agree.
I wonder what went through your mind when you found out that you had been awarded the Turing Award, and also your perception about the state of machine learning at that time.
It was a bit of a shock and disbelief at first, because I was in France when the head of the committee, Al Spector, who was the head of the award Turing Award committee at ACM, was trying to reach me, and I was not answering my phone. I was in France, with the time difference or whatever. And eventually I managed to be aware that he was trying to reach me, and so he reached me, but I didn't know why. And he told me, I called you to tell you that you won the Turing Award. I said, this is a joke. He said, no, it's not a joke. And that was certainly a bit of a surprise.
Actually, if you had emailed him, if he had emailed you, perhaps you would have thought it might be a spam or way to get hold of it. But
it actually happened with a more recent prize that okay. I didn't see it right away.
But to me, it's obviously I'm not taking away from your work. It's remarkable work. But the idea that computer science would honor somebody in machine learning with this award,
yes,
I thinking back, I said, wow, this machine learning has come of age.
No, I agree.
Yeah.
And I have a bit of an imposter syndrome as far as computer science is concerned. I do not see myself as a legitimate computer scientist. My undergraduate degree is in electrical engineering. My PhD is in sort of...
Yeah, and be careful. This podcast will be viewed by hundreds of millions of viewers. So don't
I realize that.
Don't say you have imposter syndrome.
I realize that, but I never learned like all the things that at least North American computer scientists consider core computer science. You know the algorithms, complexity theory, systems, all that stuff. I never studied this, right? So I have a hard time in like viewing myself as a card-carrying computer scientist. And so that was even more of a shock for that reason. And there's a lot of departments within CS departments within the US where, at the time, certainly machine learning and certainly neural nets were seen as kind of a little bit outside of the core, if you want, of computer science.
So I also want to just have you look back on the history of machine learning and deep learning in particular. 4 decades ago, this idea of using neural networks was very, very esoteric. Today, it's mainstream. With some probability, our next-door neighbors would know what deep learning means. I wonder if you can reflect on that. How did this suddenly happen? I mean, it didn't happen suddenly, of course. It happened over 4 decades. But still, the fact that it's mainstream, it's a household term, that to me is still shocking.
It is shocking to me, particularly when I get stopped on the streets in New York or Paris by people who want to take selfies with me. So it's not just a household term. It's it's impacting everyone's life. AI is everywhere, right?
Yes.
But the fact that there is kind of progress in the science that are attached to this that people can identify, I think is good. Makes people realize really how the sort of technology that they use every day comes about. It's not like they don't come from the sky. Rather, it's real people who invent those things, and I think that's not recognized enough. Mm-hmm. Even for engineering students, right? What you learn in first year of engineering studies or computer science, someone came up with this idea and published a paper about it, and maybe won a prize for it.
Yeah. So again, looking at the field today, the hottest thing today is large language models. That's what people, when you say deep learning, they think LLMs and they think of all these chat tools and so on. On the other hand, you've gone on record saying that LLMs will be obsolete in 5 years. I wonder if you can say, and again, this is mostly for our students who are looking for thesis topics and we're trying to figure out if this is a viable route for them to pursue in AI. What advice would you give them?
So I'm being deliberately provocative when I say this, right? And perhaps a little bit excessive. But basically, in my view, LLMs are a very useful development in AI. Obviously, a lot of people are using them. There is a lot of things to develop on top of LLM to make them better, to fine-tune them for particular vertical applications. There's a whole industry around it, which there's no issue with this. Where I have an issue is that I don't believe it's by itself a path towards more intelligent systems that have some level of common sense, that have sort of human level intelligence, but even animal level intelligence, right? So I joke very often that the most intelligent of our AI systems are actually not nearly as smart as a cat, certainly when it comes to understanding the physical world. So what I think is what we're missing in AI today are systems that understand the physical world, have persistent memory, are capable of planning and reasoning, but not planning and reasoning by just generating tokens, planning and reasoning in abstract mental representations of a situation. And I think that's a big challenge for the next decade in AI. And if we make progress over the next 5 years, then that will make LLM essentially obsolete. They will be replaced by systems that are capable of those 4 things. LLM will still be useful, but the second part of that answer is the fact that LLM nowadays is in the hands of industry, and several companies have hundreds of engineers and scientists working on LLMs using tens of thousands of GPUs, if not more, with engineering support, with enormous amounts of efforts, and it's very difficult for an academic group or PhD student to contribute to this, other than by kind of analyzing why they work, but it's kind of boring a little bit. So I think what academia should be focusing on is the next generation of AI systems that are capable of understanding the physical world, for example. And in my opinion, that will require drastically different architectures from the ones that are currently fashionable in the context of LLMs.
Do you feel that there's a gap between where we are today in academia and industry? Of course, the answer is yes, obviously. But the real question is the gap widening? And is it getting harder and harder for academia to play catch up?
Well, I don't think academia should even consider playing catch up. There's no way to really catch up in that domain by working on LLMs. Now, in the context of AI, I think a lot of innovative, good ideas have come and will come from academia, at least if academic research funding still exists in the next few years. So I think academia has a very important role to play. What is missing really is computing resources. It doesn't have to be at the same level of scale as we have in industry, but there is a need for decent sized GPU clusters for in the hands of academia. And some countries around the world have kind of national programs for this, where they make those facilities available. Europe just announced a big program along those lines. There's not been such a program in the US, unfortunately. And so some universities like NYU, like I just learned Penn, Princeton have kind of built clusters for that purpose. But I think that's required on a bigger scale.
That's a great point. I think academic investments may not be as focused, and AI certainly qualifies for these kinds of investments. I want to come back to something you said about your cat, and I think when you have AI agents in the physical world, the fact that AI relies on large data sets put AI systems in the physical world at a disadvantage, because we clearly don't have that kind of those kinds of data sets in the physical world. I don't know what you think about the catch-up problem there in terms of creating these large data sets and learning from them.
So I actually disagree somewhat. This is something I've said publicly several times, but I think it's an interesting exercise. If you take some of the largest LLMs that are trained today, like Llama, Llama 4 has been trained on the order of 30 trillion tokens, right? So 3 10 to the 13. Each token is about 3 bytes, so that's about 10 to the 14 bytes. This represents a big proportion of the publicly available text on the internet. It would take any of us on the order of 400,000 years to read for any single person. Probably more, actually. Now, compare this with a 4-year-old. A 4-year-old child has been awake a total of 16,000 hours. In the course of those 16,000 hours, how much data has come through the brain, through the visual cortex? And the answer is about 10 to the 14 bytes in only 4 years, as opposed to 400,000 years. The reason is that vision is a very high bandwidth modality, similar to touch. Actually, touch is also very high bandwidth. Audio a little less. And we have 2 optic nerves, each of which has 1 million nerve fibers, each of which carries about 1 byte per second, and do the arithmetics, and you get to about 10 to the 14 bytes in 16,000 hours. Now, 16,000 hours is not a lot of video. It represents roughly 30 minutes of YouTube uploads. We have way more video data than we can manage with learning systems. The main challenge there is not the amount of data. It's and we can generate also synthetic data, but in simulated environments with robots and with action and things like that, right? What we're missing is good techniques to train a system to understand the physical world by observing video or maybe interacting in a simulated world or maybe the real world. We don't have good techniques that work for this. The techniques that work for text do not actually work in the context of video. And the reason is the main qualitative difference between language and the real world is that language is discrete, right? It's a sequence of discrete symbols. When we train an LLM, we train it to predict the next token in the text, but really what we train it on is that we give it a sequence of words or tokens, and then we train it to just reproduce its input on its output. We call this an autoencoder. But because of the architecture of the system, it cannot cheat. It cannot use the one input to predict the corresponding output. It has to predict it from the previous ones. And so that constructs a system basically that is trained to predict the next word or the next token. It works in the context of text and discrete sequences of symbols because you can never predict what word follows a sequence of words, but you can predict a probability distribution of all the possible words in the dictionary. Now, if you want to translate this to the context of video, take a video, stop it, and then train a big neural net to predict what's going to happen next. We don't know how to represent probability distributions over, snippets of high-dimensional continuous signals like video. We just don't know how to do it. It's a mathematically intractable problem, actually. And so we have to invent new techniques that are not generative models to be able to deal with video. I made proposals along those lines. I call this JEPA, that means Joint Embedding Predictive Architectures. And basic idea is to learn abstract representation so you can make predictions in that abstract representation space. That's what I've been working on for the last number of years, and we're making progress in that direction.
Yeah, so what you're hinting at is that even the fundamental representations in terms of tokens is not powerful enough, and we have to rethink how the systems are represented, not much less the architecture, the algorithms piece.
Right, and it's it hits on something that roboticists have been very familiar with for many years, called the Moravec Paradox.
Yes,
right, where Moravec many years ago said, why is it that we can get machines to play chess, which is one of the most complex kind of intellectual tasks that humans could do, but then we can't get a robot to just grab an object. Now we can to some extent, but still we have a lot of issue. It turns out the physical world is just much more complicated than language and the world of computation.
It's continuous and high dimensional makes it a lot challenging. So let me ask you to speculate about the future and where this technology is headed. So if I were to mention AGI to you, what would be your reaction?
I don't like this phrase, AGI, artificial general intelligence. It's predicated on the idea that what it really means is human-level AI, right? AI systems that have the same intellectual capacity as humans, if not better. It's predicated on the hypothesis that human intelligence is general. And that's just false. Human intelligence is very specialized. We have a hard time accepting the fact that it's specialized because all of the problems that we can apprehend are problems that we can apprehend. There is a whole world of problems that we have no idea that we could possibly solve. And so we think we have general intelligence. We just don't. So I prefer to use the phrase AMI, which means Advanced Machine Intelligence, or AMI. If you pronounce it in French, that means friend in French. I think it's more appropriate.
I love it.
But one point I want to make, there is no question in my mind that at some point in the future, we're going to have machines that are as good or better than humans in all the domains where humans are good. It's not going to happen next year. It's not going to happen in 2 years. We might make some significant progress over the next 5 years. It's probably almost certainly harder than we think. So before we reach human-level intelligence, we're probably going to have to go through like rat level and cat level or something like that, maybe over the next decade. And then it's going to take some time after that to really reach human intelligence. And that will require scientific breakthroughs. It's not just a matter of technological advances in engineering and scaling up current technology and having faster computers and more data sets. It's actually kind of coming up with new fundamental concepts about learning.
So maybe I can press you on this a little bit. Machines are already superhuman along narrow axes. Like you mentioned chess playing. We can build machines that can run faster than the fastest human being. We can build drones powered by AI that can fly faster than human piloted drones. But isn't the idea of AGI that you somehow wrap all these axes together and you perform in a superhuman way with everything combined? That's what people are hinting at.
Yes, indeed. It's true. But for any particular domain or narrow area, there's always going to be one ad hoc solution that's going to make machine perform, maybe at superhuman level in that domain. That's basically the history of computer science. Not just AI, just all of computer science. And we're familiar with this, right? We have, gadgets, $30 gadgets you can buy at the toy store that can beat you at chess, right? So, it's been around for a while.
Yeah.
So the question is, is there a sort of unifying underlying principle that would allow a machine to be good or to learn to be good really quickly at all of those tasks? Why is it that, we have AI systems that can pass the bar exam. We still don't have domestic robots, right? We have efforts going back 15 years of trying to get, going back 40 years actually, trying to get cars to drive themselves. We have millions of hours of training data of self-driving cars for cars being driven by humans that we could use to train a machine learning system. We still don't have completely autonomous level 5 self-driving cars, except companies like Waymo, but they use all kinds of exotic sensors like LiDAR, and it's a managed fleet, and there's a huge amount of engineering, and the cars can only work in areas that are completely mapped, and there is human operators that can be called if the car gets stuck. So we don't have compare this to the fact that any 17-year-old can learn to drive in about 20 hours of practice. Mm-hmm. Okay, obviously we're missing something really, really big, and that's what I'm after. That's I'd be really happy if, by the time I retire, which may be coming soon, we have some decent way towards, system that really learn how the world works like babies, by watching the world, interacting with it a little bit, and really understand a lot about the world, mostly by observation, requiring a small amount of training data, really.
Let me ask you a last question on perhaps the macroeconomics of everything. So do you worry about AI and future advances impacting jobs? And there are a lot of claims that it'll have a $1 trillion impact, $3 trillion. Depending on which consulting company you reports you look at, you have all these projections. You ever thought of that? And do you think any of these are realistic?
Okay, so I'm not an economist, first of all, but also a lot of those predictions are made by people who are not economists. If you talk to economists whose career has been built around, or whose expertise is the effect of technological revolutions on the economy and the labor market, people like Philippe Aghion in France, like Eric Benioffson, who was a student with Philippe at MIT, who is now a professor at Stanford, and a bunch of other people, they have a very different language. So first of all, they're telling you AI, like every other technological revolution before it, will not create mass unemployment. So the idea that somehow, robots are going to do all our work and we can stay home and most people are going to be destitute because they don't have a job, that's just not going to happen. Eric says we're not going to run out of jobs because we're not going to run out of problems, which I think is interesting reflection. So that's the first thing. The second thing is, could there be like $1 trillion business? Sure, if we have, human level intelligence in robots that can do most of the jobs, the economy will look very different and will expand. The productivity of individual humans will augment. They're not going to replace humans. Humans are going to be their boss, right? So the future in which we have super intelligent machines, whether they are physical robots or whether they are kind of virtual assistants that live in our smart glasses or something like that, they'll be with us at all time. It's as if all of us would be working around with a staff of virtual people who are smarter than us. And you and I are professors. We're very familiar with working with people who are smarter than us, or students. It's the best thing that can happen to you. We shouldn't feel threatened by this idea, or intelligence is going to be amplified by it, right? And our productivity and possibly our creativity also is going to be amplified by it. So this is, certainly, maybe in the best of all possible scenarios, this may create kind of a new renaissance for humanity, right? Similar in the effect of the effect of the printing press, perhaps in the 15th century Europe. But you have to be very circumspect about the actual effect. So, for example, Eric and Philippe Berguillon have tried to compute how much increase in productivity will result from AI over the next few years, in GDP growth or something like this, and it's on the order of 0.7% additional, growth in productivity. It compounds over time, so it's actually big, but it's not enormous.
Well, something tells me that you're not going to retire soon, and something tells me you're going to be busy with fundamental problems to advance the state of AI. So, Yann, thank you very much for sharing your opinions, your expertise, and thank you for the contributions to the field. You really put AI on the map to success. So, thank you again for joining us.
Thank you, Vijay.
It's clear that the future of AI is as complex as it is promising. And hearing it from someone at the very forefront of that future has been truly inspiring. Please subscribe to Penn Engineering's Innovation and Impact podcast series on your favorite podcast platform. We'll see you next time.